So geometric, you guys, is really similar to binomial. That's why we're grouping them together here. Very similar. So the goal is to repeat a chance process until a success occurs. That's what a geometric random variable is. You do something over and over again until you get the desired outcome. So here's an example. You roll a pair of dice until you get doubles. In basketball, attempt a three-point shot until you make it. Keep placing a $1 bet on the number 15 in roulette until you win. Okay? So everything is the same except for the end part of bins. So you still have to have bins be true, like in a binary. You still have success and failure, okay? You still have independent trials, same thing, or the 10% rule. The only difference is that the N, they changed it to a T for bits. And I don't know why it's a T, but it's until, so I'll put a capital here, you get the desired outcome. I know, right? You can still think of it as bins, just know that geometric is until you get the desired outcome. All right, so there's not a fixed number of trials. You're going to keep going until you roll doubles or whatever. So probability of success has to remain constant each time. So, is this your lucky day? Your teacher is planning to give you 10 homework problems for homework. As an alternative, you can agree to play the lucky day game. Here's how it works. A student will be selected at random from your class and asked to pick a day of the week. For instance, Thursday. Then your teacher will use technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will have only one homework problem. We're not done. If the student picks the wrong day, your teacher will select another student from the class at random. The chosen student will pick a day of the week, and your teacher will use technology again to choose the lucky day. If the student gets it right, the class will have 2 homework problems. You got it right on the second try. The game continues until a student correctly guesses the lucky day. Your teacher will assign a number of homework problems that's equal to the total number of guesses made by members in your class. Oh.
70 cents for real?
No, this isn't for real. I know, this is the example that was given, so I was like, you guys want to play the game?
Yes.
All right, hold on, let me get a
Oh, yeah!
Okay, here we go. Geometric settings and random variables. So the random variable of interest in this game we're going to define as y, the number of picks it takes to correctly match the lucky day. Each pick is one trial of the chance process. Knowing the result of one student's pick tells us nothing about the result of another pick. On each trial, the probability of a correct pick is 1 out of 7. This is the geometric setting. Because y counts the number of trials to get the first success, the geometric random variable has a parameter of 1/7. So just to check bits real quick, right? Bits. Binary, you guys? Yeah, you either win or you don't win, right? Either got it right or you got it wrong. Independent, they just talked about that. Yep. Okay. T for until you get whatever the correct pick is. And the success would be the probability, which is 1/7. Okay? So you do want to check that for geometric. So this is a formula you get to use, geometric probability. It is not on the AP exam. However, this is the same thing as like the multiplication rule that we did, right? So what happens is you're going to take the probability here of failure, because you're going to get it wrong a certain number of times, okay, until you get it right. So 1 minus p, that's the probability of failing, right? 1 minus p. So if we have a 1 in 7 chance, that means every single first one of getting it wrong is a 6 in 7 chance. We get a 6 out of 7 chance of getting it wrong every time. Okay? Till a certain number of trials, this is how many times you got it wrong. So that's why the last one is only to the first power, because this is the probability of success right here. So a 1 in 7 chance, and then you're done because you got it right. Make sense? So it's always the probability of failing over and over again until you get it right, so times the probability of success. So K would be, I want to get it right on the 5th time. I want to get it right on the 6th time. Okay? Sometimes they're going to ask you what the probability is of getting it right on that trial. Yeah. So here's an example. Find the probability that the class receives 10 homework problems as a result of playing the Lucky Day game. All right. So probability that y is exactly equal to 10. So we're going to use the formula. So in the first part, it's 1 minus p. The probability of not getting it right. What is that in this case? 6, 7. And how many times are we going to get it wrong here if we want to get it right on the 10th time? 9, right? 10 minus 1. So we're going to put a 9 here. You have to get it wrong 9 times. And then we multiply times the probability of success, which is 1 in 7. And it's always a first power there because the last time you get it right and you stop playing. Okay? So multiply that out and you get 0.036. There is also, of course, a calculator feature. Isn't that nice? As there is in like everything in stats, it seems like. So, geometric probability is on your calculator. You find it in all the same place you find everything, right? We go to menu on the Inspire, and then we go to statistics, right? And then we go to distributions. Just following along here. And this one would be geometric PDF. Remember, if we're doing it one time versus a whole, adding up a whole sum of them, the C for cumulative. So geometric PDF. And what comes up as what you have to fill in when you do geometric PDF? Let's see. PDF. So we got first the probability of success is 1/7. And the x value, so when you want to actually get it right, is 10. And we should get the same answer. Okay? So you should probably play the game, right? Because that's a pretty small chance that you're going to actually have to do 10 homework problems. Okay. Part B, find the probability that y is less than 10 and interpret this value in context. Probability that y is less than 10. So this is the sum of all of those formulas, right? So we want the probability of getting it one time plus the probability, so we get it right on the very first try, okay? The probability we get it right on the second try. Probability we get it right on the third try, dot, dot, dot. The last one would be the 9th try because it's less than 10, okay? Probability of getting it right less than 10 times. So we either get it right the first time, second time, third time, all the way up to the 9th time. Again, this would be every single formula. I want you to write this in your notes. Yes, there is a button on your calculator, all right? But you have to understand the formula and know how to use the formula. So less than 10. If I want to get it right on the first try, that means we take the probability of failing, and that never happens, times the probability of it happening to the first power. Okay? That represents p equals 1. What if we get it right on the second try? Well, that means we have to get it wrong one time and then get it right on the second try. Make sense? See the pattern? So on the third one, we have to get it wrong twice and then get it right on the last try. Right? All the way up to the 9th one, meaning 6 out of 7 times we got it wrong here, 6/7 probability, but we got it wrong 8 times, and then we finally got it right on the 9th time. Okay? or our calculator, which is always a good way to go when you have those long ones. So geometric, this time CDF. Okay. This time we have to plug in the probability of success, which is 1/7, the lower bound, which is 1, and the upper bound, which is 9. If it's less than 10, you guys, don't include 10 on these. And we end up getting 0.75. Don't forget to write your sentence, which answers the question. So there's a 75% chance the class will get less homework by playing the Lucky Day game. Weren't you guys lucky? All right. So using your calculator, that's just a reminder. If you're on the 84, you do second distribution. Did you guys find it? Okay. Cool. So PDF if you have equal to, CDF if you have. I think the 84s only do less than, you guys. So then you have to subtract. Okay? Similar to the binomial one. Oh, sad. All right, the mean. This is important. So yesterday we did the mean of a binomial distribution, and it was n times p, and we did the standard deviation. We also are going to do the mean of the geometric, which is this formula right here, 1 divided by p. 1 divided by the probability. So the last problem, it's 1 divided by 1/7. And that would be the average or expected value. Hi.
So what was that?
Okay, let's check our understanding here. So, suppose you roll a pair of fair 6-sided dice until you get doubles. Let t be the number of rolls it takes. Show that t is a geometric random variable, so bits. Okay. So go ahead and think through each of those. Go through this. Binary. So let's see. David S. Is it binary? Yeah. You either get doubles or you don't. Okay. So Maddie, are the rolls independent? Yeah. One roll does not affect the next roll. And Michaela, do we have until we get a certain number of rolls? Yes. Okay. And Abby, what's the probability of success? Ooh, the hard one. Anybody know, you guys? Owen? It is 1/6. If you draw the chart where there's 36 sums, then it's 6 out of 36, which is a 6. Okay? So, yay, we have a geometric setting. All right. So now we're going to find the probability that it takes 3 times for this to happen. Okay? Use the formula. Don't use your calculator for this. If you want to double check it, fine. But this is one that would be super easy to use the formula for. Plus, you have to understand the formula anyways. So do it with the formula. All right, so Malcolm, what's the probability of not getting doubles? Okay, so we're going to start with 5, 6, because we have to not get doubles a certain number of times, right? We want to succeed on the 3rd time. So, Jake, how many times do we not get doubles? Twice. And then we have the probability of success to the 1st power, because we succeeded on that one. Okay, multiply that out, and you should get 0.1157. So there is a 11.6% probability that you will get the first set of doubles on the 3rd roll of a dice. Okay? All right. And in the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability that this happens. So not exactly 3, but within 3. If you guys want to use a calculator on this one, you can. Make sure you write down what you plug in, what each one is. All right, so we got geometric CDF. The first thing they ask for is probability of success. So Ginger, what goes in for P? 1/6. Okay, then we have to do our lower bound to our upper bound. Donovan, what's your lower to upper? 1. Yeah, 1 to 3. We're including 3. So 1 to 3. And you get 0.4213. This is the formula way, just so you guys know. There's really like a 5/6 to the 0. So you got it right on the first one. You got rolled doubles. This one would be you got it on